Alright, so in this video I'm going to be talking about the method of row reduction as applied to matrices, and this is probably the most useful method you will ever learn for solving systems of equations. So what I'm going to do is I'm going to show you how to do it with this particular example here. So we have three equations and we have three unknowns, x, y, and z. So the first thing I like to do is to expand this equation by including all the terms. So if I include all the terms here, that means that we have 0z equals 6. And I'd like to align all the variables within along each equation. So for example, this one we have z here, and this implies that we have 0x and 0y. And you will see the reason for why I like doing this. And similarly here I have y and I have 0x and 0z equals to 2. So this is a pretty straightforward procedure. And now what I like to do is I like to set up a matrix equation, so you know that we're going to take the coefficients, and now it's a lot easier for us to see what those coefficients are because we can pretty much just do this column by column here. So we're going to start with the first one. So we have 2, 2, and 0. Then we have 0, 0, and 1. And then we have 0, 1, and 0. And now we know that we can multiply this by the vector x, y, and z. And this should be equal to the vector here, 6, 3, and 2. So this is the matrix equation we're going to solve. Now, in order to solve this system, you know that if you write an equation as ax equals to b, then the solution vector is going to be given by the inverse of a times b. And you might be wondering, well, can we just invert the matrix as we learned in the previous video? Well, that would take quite a long time, especially because we're dealing with a 3x3 system, but in reality we might actually be dealing with much larger systems. And you can imagine that even for developing a computer program, we need something that is much more efficient and reliable than having to perform all the operations required to invert the matrix A. So what I'm going to do is I'm going to write down something that is often called an augmented matrix. So I'm going to ignore this vector here, and I'm going to write the matrix A. So this becomes 2, 2, 0, 0, 0, 1. And then 1, 0, 1, 0. And then I'm going to draw a straight bar here, and I'm going to put the solution, or rather the vector on the right hand side here as well. So this is what we call an augmented matrix, and it is essentially just a shorthand notation for a matrix equation of this form. Now we're going to perform some operations on this. So there are three main operations that we can perform with respect to matrix equations like this. We can multiply a row by any constant. That constant can be a real or a complex number, and it can also be negative or positive and also rational number. So it can really just be any constant that you want. So for example, you can grab this first row and multiply every element in it by a constant like 2. So that's something that is allowed, and we can perform that many times on any row that we choose, but it can only be done by rows. So we cannot do the same kind of operation along columns. So row reduction really is operations made onto, or operations rather performed on the rows of the augmented matrix. Notice that if we do that, every single element here changes, including this one, and that's a really important thing. Second kind of operation we can perform is swapping rows. So we can actually swap two rows together at any point. So for example, I can grab this row here and exchange it by the top row, or even the first row here, and I can continue doing that as many times as I want. So that's also an allowed operation. And the last one is we can add or subtract one row from another. So I can pretty much just grab the first row, for example, and subtract it from any of the other two rows, and I can continue doing that as many times as I want. Now, what's the ultimate goal of row reduction? Well, we want to get to an expression that looks like this. Ideally, if we have a 3x3 system, we want everything else to be a 0. So we would have something like A, B, and C here. So depending on what operations we perform to make this 1, 1, and 1 as we have here, we're going to have some 3 constants there. And the reason for this is that this would correspond, if we expand this system now, this would basically mean that x equals to A, y equals to B, and then z equals to C. So we have already solved the system if we find a way to express it in this form. So that's a really useful thing that we can do. Alright, so now that I have defined some of the main properties and some of the operations we can perform, let's actually apply row reduction to this matrix here. So row reduction, we usually write it with a long arrow. Sometimes people use a squiggly line like this, but we need some space to actually write the operation here because it is good to show the kind of operation we have done because sometimes it may not be so obvious. So the first thing I would like to do is I want to grab the first row. So I'm going to do row 1 prime, which means that this is going to become the new first row. And we're going to plug into that row the following value. So I'm going to divide the previous row 1 by 2. So that means I grab these values, divide each of them by 2. So this becomes 1, 1, 0, and 3. And everything else stays the same. So 0, 0, 1, 0, 1, 0. And then this stays as 3 and 2. So we have now performed an operation on our augmented matrix. The next thing we're going to do is, let's say that I grab row 1 again, so row 1 prime, and now I'm going to subtract row 3 from row 1. So basically I grab this row, subtract it from the top, so this becomes 1, 0, 0. Then we have 3 minus 2, that becomes 1. We have 0, 0, and 1 here, and then we have 0, 1, 0, 3, 2. So this is pretty much what we would be saying here. And now if you notice, well, we want the leading terms, we want the ones to basically follow this kind of diagonal pattern here. So we want the ones to be laid out across the diagonal of this matrix. So in order to do that, what we can do is we can swap this row and that row. So basically that's what we're going to do. So let's say that we swap row 2 with row 3. And that means that we can now write 1, 0, 0 and 1, 3, 2. And then here we're going to have 0, 1, 0. Actually, I made a mistake because remember we're swapping rows. So that means that this should be 2 and this should be 3. This should be 0, 1, 0 and then 0, 0, 1. So now we have this form. This is what we call the reduced row. So let me just go down here. Reduced row echelon form. So that's basic. That basically means that we have set out our columns in such a way that there's always a leading one across some row, and then everything below it or above it is a 0. So that's what this form means. So now that we have this, we can expand this out and we can say, well, x, y, and z are going to take on the values of 1, 2, and 3. So that is the solution to this original system of equations we started with. So you see that this is a really useful method, and in fact it works for not just for systems that have the same number of unknowns as number of equations. It actually works for any system of equations. So we could have something like 3 by 4, we could have like 4 unknowns and 3 equations, or 4 equations and 3 unknowns, and this would still work to some extent. We wouldn't get a single unique solution, but we would still get an idea of what the set of solutions would look like, which is quite useful in both engineering and science and applied mathematics in general. So in the next video, we're going to extend this by working a different example in which we don't get a unique solution like we did here.